I'm going to talk about interdomain security, which means how do I know that someone is the right holder of a particular IP address and how to secure BGP. Okay, that's the focus of my topic. And I will do that trying to see how blockchain can play a role there. Okay, so I'm trying to apply blockchain to interdomain security. Now, just in case someone in the room is thinking, but wait, blockchain is Bitcoin. Bitcoin has many issues. There is lots of energy being wasted. I have read many bad things about Bitcoin. You are correct, but this is not. I'm not applying Bitcoin. Okay, blockchain has many other properties. This is not related with Bitcoin. There are many other alternatives on how to implement blockchain. So we are not using Bitcoin. We don't need huge amount of farms of energy to run our network, just to clarify this. So I would like to start first explaining which is the state of the art in interdomain routing security. Okay, so the main thing that we want to do is we want to authenticate that a particular IP prefix belongs to an organization. How do I know that this particular IP address belongs to Google? Okay, and the way it is done right now is that the registries, they issue a certificate which states, okay, this prefix belongs to this guy. Okay, then with this certificate, the organization builds another certificate which goes to the router, which says this router is allowed to announce this autonomous system. So you are binding the prefix to the autonomous system, and then the router, the BGP speaker, will announce the prefix with the AS number. Then all these repositories, all these certificates, they are stored in a repository where I can retrieve them to verify that my BGP update that I have received is correct. And finally, there is a fourth aspect, which is, okay, with this, I'm securing the origin of the update, meaning I know that this particular AS number has this particular IP prefix, but I'm not securing the path. So for this, the state of the art is something which is called BGPsec, which is that each BGP announcement along the path is signed by the router. Okay, so this is pretty much a quick summary of the state of the art. Now, I would like to explain a little bit how blockchain works. I'm sure that many people in this room already know this, and I apologize in advance. It will be very quick, just in case someone is not very familiar with blockchain. So blockchain is a distributed database. Okay, it's a distributed database which is append-only, meaning that I can only add new information into the chain. Now, why it's secure? Well, it's secure because the participants will have to reach a certain consensus and agree that new information should be added into the chain. Okay, so the chain we can only add information into the chain if the participants agree that the information that is going to be added is correct. Okay, and that's what it makes this secure. The way it works is that I build a transaction, which, let me use the financial example because it's very simple. Let me use Bitcoin, although, as I said, this is not related to Bitcoin. But let's say I want to send some money to someone. What I will do is build a transaction. I will put my own public key, which is identifying me. I will send the transaction, and I will say I'm giving this guy this amount of money. Then what I will do is I will broadcast this transaction to all the participants. Then someone, which is typically called miner, will gather all the transactions and will create a block. It will gather all the transactions and build a block with all these transactions, and it will add the new block to the chain by running this consensus algorithm, which is very relevant, and I will explain later. Once this new block has been added into the chain, I will broadcast the block to everyone, and everyone will verify that everything is correct and that the consensus was correct. So the main advantages of the chain, and I will talk about the consensus algorithm, is that, well, there are many advantages, but for our scenario, I think that two are the most important one. The first one is that you don't need certification authorities. Okay? So typically, in a public infrastructure system, you have one certification authority which has all the power and all the trust. In this case, no one has all the power and all the trust. Okay, so it's a decentralized trust system, and I think that this is one of the most important aspects. The second one is that typically public infrastructure systems are quite hard to manage. And this is quite well known. They are very cumbersome. You have many certificates. They are very expensive. Now, blockchain has many advantages in terms of management. So it is cheaper to run a blockchain than a traditional public infrastructure. Those are the two main advantages. And one of the most important drawbacks, and we should be aware of that, is that it does not offer cryptographically guarantees, meaning that in a traditional public infrastructure system, if you trust the certification authority, you have a cryptographical guarantee that the information is valid, that no one has modified this information or that the information is confidential. Now, in blockchain, you don't have this guarantee. You rely on the consensus algorithm. So what you are trusting is the consensus algorithm, which typically does not offer cryptographical guarantees, but rather social guarantees, which are a little bit harder to assess. So let me talk about the consensus algorithm. So it's the most important aspect of any blockchain because it's where the trust is and defines how we add new blocks, which are the rules that we all agree that we will respect when adding a new block into the chain. And I will discuss two of the most important ones, which are proof of work, which is the one being used in Bitcoin, and the ones we use in our chain, which is proof of stake, which is shortly will be used by Ethereum. But there are many others, and the literature goes on and on. There are many, many ways to achieve this. So the way Bitcoin works is based on proof of work. And the idea is that when we want to add a new block into the chain, we need to run a very complex calculation, which is basically solving a mathematical problem which consumes lots of CPU and lots of energy. And once we solve this mathematical problem, we add this information into the block, and we send it. So how this makes Bitcoin secure? Well, the thing is that as the chain grows, it includes more and more CPU. So you need more and more CPU to compute it. Okay? So it is storing CPU cycles and CPU energy. So if someone wants to build a new chain and change something, it needs to redo all the calculations, which is very expensive. And fundamentally, Bitcoin depends that the good guys have more CPU power than the bad guys. So as long as the good guys have more CPU power than the bad guys, the chain is secure. So this is what I was referring to. You are trusting that the good guys have more CPU power than the bad guys. Is this true or not? Well, I don't know. Then you have other consensus algorithms. This is the one we are using, which is proof of stake. This one is very simple, and the idea is that I will build a table with all the participants, and I will put into the table which is the amount of assets that they hold. Let's say that this is a cryptocurrency. How many coins they do have? Or IP prefixes. How many IP prefixes do they hold? And then I will throw a random number. And I will weight this random number based on the amount of assets that the participants have. The more assets they have, the more chances they have to be elected. And I will pick one randomly, which means that the chain is built. The chain depends on the participants that have more assets in the long term, statistically. This does not mean that the participants that have few assets will never add a block. It means that statistically they will add less blocks, and those guys will add more blocks. The idea behind this is that the participants that have more assets are more invested into the chain, and they have more incentive for the well-being of the chain, which is an assumption that may hold or not may hold. But this is what proof of stake is about. OK, so after this introduction, let me go and explain what is our proposed blockchain. So what we want to store is information regarding who owns a particular IP prefix. So it's the same thing as RPKI is doing. So what we want to store is information about, OK, this prefix, this is the holder of this prefix. And we also want to store information of prefixes can be delegated. So in order to hold a prefix, I need a registry to delegate it to me. And as a company, I can further delegate it to another part of my company or to another company. There are some rules for this. So I want to store all these delegations. And finally, I want to store the bindings between the prefix and the AES number, just as RPKI. And the way we do it is we pretty much assume that IP addresses have many properties as coins. And if you think about this, it makes quite a lot of sense. So IP addresses are unique. You cannot have two entities having the same IP prefix, which is exactly the same as coins. You can transfer them. So IP addresses can be transferred between the registries and an ISP, between an ISP and a branch from the ISP. And you can divide them, just as coins. You can take a prefix, divide it, and give and delegate one subprefix to another branch from your company. So we assume that we can exchange block of IP addresses just like coins. And for this, we use proof of stake. By using proof of stake, what we are saying is that the guys that have more prefixes will be in control of the chain statistically. And this is a thing that is open for discussion, but the point we're trying to make is that if a company holds many prefixes, this means that it is heavily invested on the internet, and it is somehow making money out of the internet. So it is incentivized to the well-being of interdomain security. This is our thought, which may hold or not, but this is the way we approach it. So how does this work? So the first allocation comes from Ayana, and Ayana will say, OK, I own all the IP prefixes. Let's assume that we only have IPv4. So it will write a new block, which is I have all the prefixes. So 0/0 belongs to me. And this is called the Genesis block. And this is a block which is trusted blindly by all the participants. We all agree that this is true, and that's it. There is no way to make sure that this is correct or not. We all agree that this is true, which in fact is true. Then Ayana will add a new allocation, will add a transaction, which is like sending money, but in this case, it's sending IP prefixes. And it will say, OK, I'm going to send 1/8 to AppNic, to a registry. So you will write this transaction into the chain. Then AppNic will add a new transaction, which is I will allocate 1.2/16 to an ISP. So you add this transaction into the block. Now that the ISP owns the prefix, cryptographically owns the prefix, it will bind this prefix to a particular AES number, which is his own AES number, and will say, OK, I am 1.2/16, and I am AES number 12345. Okay? Now, ISPA will start to BGP update and announce this prefix over the internet. And let's say that we receive this prefix. We receive a BGP update binding from this AES number, from this AES number and in this prefix. So what I can do is I can go to the chain and try to verify this. And how I will verify it? I can work back the chain. OK, so I have received a BGP update that says that 1.2/16 is in this AES number. Is this correct? So, well, this prefix was, this was signed by ASPA. ASPA was indeed given this prefix by AppNic. I can work back the chain and say, OK, but I don't trust AppNic. So this prefix belongs to AppNic and actually was given by Ayana, and I'm trusting Ayana. So I can work back the chain and verify that everything is correct, as long as I'm trusting this first block, which is quite reasonable. Okay, so this is the way, simplified, how it works. So which are the main advantages of this? And I will insist on this over and over and over. The first one is that you don't have any more central authorities. So let's say no one has full control over the prefixes and interdomain security. Okay, you have distributed trust and you have distributed the power. And I think that this has many implications, which I will insist afterwards. And another very important aspect is that with certification authorities, your security depends on the security of the CA. If the CA loses its private key, you are screwed. You have a huge security issue. With this approach, you cryptographically own the prefix. You are the only one that can screw things up. And that's something that typically is a good thing. You don't depend on, your security only depends on you, not on the certification authority. And then a second aspect, which is a little bit harder to explain in this slide, but please trust me, it's a big issue, is that in public key infrastructure, management is really, really complex. It's really costly because you have certificates, you have private keys. Rekeying is a huge mess. Rekeying for the certification authority is even harder. Revocation is also a big deal. You have to distribute certificate revocation list. Now, this is greatly simplified with blockchain. And finally, you have auditability, since everything is written on the chain, and you know everything that has happened with a particular IP prefix. So those are the main advantages. So we did some experiments in this work. We built a prototype, which is quite fully featured with Python and proof of stake. And what we did, we took all existing IPv4 BGP prefixes on the internet, and we pretty much added them into the chain in the same way I'm showing it here. And we wanted to understand if there are some implications from the implementation perspective that are relevant, which is the performance. Well, we wanted to prototype it. You have all the details on the prototype here, which is open sourced. You have the paper that provides all the details, and we also have an ITF draft if you want to have further information. I don't want to show all the plots that academics like to do, but a question that I get very often is this one, is, okay, which is the size of this chain? It is very large. Well, if we account for 140 prefixes, which is right now what we have in IPv4, this is around 1 gigabyte, which is it's quite reasonable. You can store this pretty much even in a phone. Okay, so it's not very large. But that's true. This will grow indefinitely, just as Bitcoin. Okay, but so far it's not very large. Now, and this is, I think, or I hope the part that at least I want to emphasize as the most important one. So we took this idea and we went to RIPE, we went to ICANN, we went to ITF, we talked to many people, we talked to ISPs, small ISPs, large ISPs, content providers about this idea. And here I want to be very honest about the feedback that we received and what did I actually learn about this. So the first thing I learned is that the consensus algorithm is really crucial. And I think that we should have an important debate regarding this. Let me elaborate on that. So let's say that you want a fully centralized system. So you want one guy, which is a certification authority, to have the full power and the full trust. Okay? This is what we have today with public key infrastructure. This is a standard one. Now, what blockchain provides is a way to move from this model where trust and power is fully centralized, meaning that the certification authority, in this case, IANA, has all the power, to a model where power and trust is more flexible and is distributed. If you go to the fully distributed side, you will see that we have here two consensus algorithms, which is proof of stake and the one that we propose, proof of work and proof of stake. In this case, trust and power is fully distributed, meaning that no one has full control over the network. Okay? Is this a scenario ideal? I don't know. I think that that's a big discussion to understand this. My very personal and subjective opinion is that this is not maybe the best idea. But the point I'm trying to make is that we don't need blockchain allows us. Before blockchain, we were here always here. Now we can move here and decide where we want to be. Now there are other consensus protocols, such as Stellar or Hyperledger, which are in between. In this case, you are not fully distributing the trust, and you have few nodes which have some control over the network, and you are trusting them. But it's not just one entity. Okay, and maybe this makes more sense for the internet scenario. But I don't know. I think that that's something that we should debate. The point I'm trying to make is that we can be anywhere we want. Before, this was not. I'm not saying that this was not possible, but this was very difficult. What blockchain allows us is to be here. Where we want to be, it's up to us to discussion. So what I wanted to say is that blockchain provides flexible trust and power. we need to decide where we want to be. If we want to be on the fully centralized, that's fine. But when talking to ISPs, small ISPs, they didn't care that much about this. But large ISPs and large content providers, for them, their prefixes, IP prefixes, are very important for their business, and having full control over them was an important aspect. And the fact that your security depends on another entity is something that they don't like. This was more or less the feeling I was getting. So they were more open to these kind of approaches where they feel that they will still have some power over their prefixes. So proof of stake is a fully decentralized alternative. Maybe it's too decentralized. That's a feedback that I also received. And maybe a semi-decentralized model works better for the internet scenario. Then the second big lesson that we got was that the deployment of RPKI is around 7 to 8% right now. So 7 to 8% of the BGP prefixes are protected by RPKI. And BGP-SEC is not being deployed. And there is no clear path to deployment. There are many issues because you need to change all the BGP speakers. BGP speakers need to sign BGP updates. So it's quite complex. But when talking with people and asking them, OK, why you have not deployed RPKI? It's because you have trust issues with RPKI? And most of the answers, particularly with the small guys, was, no, it's that I don't have any incentive to deploy RPKI. So I need to spend some money into this, and I'm not getting any revenue. So this is too complex to me. I'm not going to have my prefix deployed. Even that the registries are doing a fantastic job reducing the deployment cost of RPKI for a particular prefix, they don't see it as an alternative. BGP-SEC deployment cost is way too high, and that's why it's not even taking off. Like deployment of BGP-SEC is like close to zero, and it has some other security issues. So the feedback I'm trying to give is that if we want to approach this issue, trust is an important aspect, but we need to find incentives. We need to find ways to provide incentives to the people that need to spend some money on this so that they can see some kind of either revenue or something that they don't see it as a cost. Otherwise, this is also very complex. And I think that any new proposal should take this both things, trust and incentives, into account. So that's pretty much it.
Is there any questions from the room? Yeah, go ahead, please.
Thanks. Where's the cost coming from in the adoption of RPKI? Is it that the router vendors are demanding some money for a software update? What's the cost?
No, there are several ways to deploy RPKI. One is where you hold the certificates, and you have to generate a private key and sign all these certificates. This means that you as an organization need to generate a private key, which is secure. You need to store it. You need to keep it secure. So the answer by some registries, what they are doing is they are saying, don't worry, you don't need to generate any key. I will generate your private key, and I will keep it. But then there is no security. You are trusting the registry to a point that it doesn't make too much sense. So even if when the deployment cost is very, very low, since you don't hold your private key, it does not make any sense to me. When you have to hold your private key, well, you need in your organization, you need to say, you define a protocol, how you generate the private key, who stores the private key. And then BGP-SEC is out of the question. You need to change all your routers.
Well, I was this morning at 11:45 on a panel about network transformation for business transformation, and you should look at it. It's interesting. So it's recorded. And the keyword which picks on me here is the word incentive, which is a business word from the business domain. So isn't it enough incentive when we want to buy, to build, I'm from Deutsche Telekom, by the way. If we operators want to build for 5G a network and everything, that we don't have to throw it away after 2 years because of some attacks found out that the whole architecture is wrong. So we need to put in some incentive simply to that people do this. So it's as simple as that. My solution would be call for action, Release 16, 3GPP, define a fucking incentive.
So that's a good question. I think that the question should go to you. I'm an academic and you are the operator.
Yeah.
But jokes aside, so I think that the small guys, they have a different view. The small guys, they see this as a cost and they don't see incentives. Large guys, like Deutsche Telekom, they typically see incentives, but this is like a very old question. So, and maybe the previous Jerome can also chime in into this discussion. What are the incentives of security? The incentives of security is preventing an attack, which is a cost that may happen in the future. But there is no revenue right now. And I think that this is where we are having issues with maybe management that has to approve that. So I think that this belongs to a broader debate, and I don't have the answer for that. But the truth is that this is not taking off. So the current state of the art for interdomain security is not taking off. That's a fact.
Yes, but then we have to do something. And anybody in the audience or here or wherever, I like to ask, in the Metro Ethernet forum, they have announced that they are working on a protocol, how you can signal from the as part of their Sonata or whatever interfaces, that when you want to interconnect at the Ethernet level between two carriers, they would like to signal security requirements. Yeah, and that would be an incentive, because an operator who would not be able to confirm that he meets a certain security level would not be able to peer. As simple as that. With another operator that says, I only peer with you if you meet my security level 17.
Yeah, I agree. I think that this is a good incentive. Yeah.
So I encourage you to look at this Metro Ethernet Forum security group to maybe support it by contribution and to get this going, because I'm afraid if we continue like this, we will not be able to have a secure 5G network.
Thanks for the suggestion. Yeah.
So, any other questions? Okay. Yes.
Yeah. I also had a question about the incentive-based mechanism. I was also thinking about the pricing. So if pricing could be an incentive as well. So if you provide, but yeah, but it's of concern for the users. So if the user has to pay more when the service is not secure, it can be an incentive for the user to always use security and to pay more attention to security.
In this particular scenario, I think that the users are very far away, because this is BGP, and I don't think that the users care or are aware of BGP, and there is no incentive. So I don't see any way to explain to a user that this is the cost is higher because BGP is secure, because they will.
I see. Yeah.
So that's.
I see. Okay.
Like peering, so limiting peering to domains that are not secure, I think it's the right incentive, but someone needs to enforce it.
Okay. So it's more on enterprise level and not on individual user level.
Yeah, the user, I think,
okay, good.
I mean, if the user, depending on who is the user. If it's the end user, definitely not. If there are other networks that are peering, then it might make sense.
Okay, thank you.
Thank you.
All right. So looks, security is a big issue here. So, but we still have a schedule. We need still going on. So for the presentation, let's stop here. So next day is a panel. So I'm going to hand over the floor to the Professor Wen. So we are going to have a panel here.